Hello students, welcome to the class of teacher Meenal Pereira. In today's video, we will study about oscillator, oscillations and oscillatory motion, amplitude of oscillation, time period of oscillation and frequency. So these are various terms that are related with sound and how it helps us to hear the sound in a better way. So let's begin. So first we will study about in the previous video we have already studied about the pendulum. Okay, so we will further go little details of this. Take a long thread about half meter long. This is a long thread. Tie a small iron or wooden ball to it. This is the wooden ball or iron ball, and suspend it from a support as shown in the figure. So this is a support, this is a thread, and this is a metal ball which is attached to it. Such an oscillator is called a pendulum. Okay, so this figure or this oscillator is called a pendulum. Now, let's give an oscillatory motion to the pendulum. What is the meaning of oscillatory motion? We are giving a little jerk to this pendulum, so it starts moving from one place to another. Okay, we have already studied in the previous video that how it completes one oscillation. This is the central position. It goes to one side, then coming central back side, and next again here is one oscillation. So we have given an oscillatory motion to the pendulum. Now let's see. The maximum distance between the original position A of the pendulum, this is the original position A of the pendulum, and the extreme position B or C is called amplitude of oscillation. Okay, so this is the central position, then this is C towards this side and B towards this side. So the maximum distance, okay, between the original position, that is A, and the extreme position B. Okay, so this is amplitude. This distance from A to B is amplitude, or A to C is an amplitude of oscillation. Okay, so AB or AC is the amplitude of oscillation, not together. Okay, it is not ACB, but only this particular distance. You can see the label. This is the amplitude or this is the amplitude. So this is the maximum distance between original position A and extreme position C. Okay, next. Now some facts. A stretched rubber returns to its original state when it is released. This property is called elasticity. Okay, so as you can see in the diagram, I'm stretching the rubber and then releasing it coming back to the original shape. When a stretched rubber band vibrates, elasticity is at work. Okay, so when you give a small jerk to that rubber band, it vibrates. So elasticity is at work. All the while that the pendulum oscillates, Earth's gravitation is at work. Okay, so you all know that the gravitational force of Earth acting on each body. So let anything happens, like the pendulum is at oscillation or the pendulum is at work, the gravitational force is acting on it. Okay. Now, next we go to the time period of oscillation. Now, as the name suggests, time period means time required for the oscillation. Let's see. The time required by an oscillator to complete one oscillation. Okay, so this is my oscillator. This is my oscillator. So the time required by this oscillator or pendulum to complete one oscillation is called the time period of the oscillator. Okay, now in this activity, the oscillator travels the distance from extreme position B to central position A, and from there to position C. Okay, so this is, now pay attention. This is the original distance. I am giving a small oscillation to the pendulum. From A, it goes to C. Then from C, again it will come to A. Then from A, it will go to B. And then when it again comes back, okay, to A, so that is the time required by oscillator to traverse the distance, that is from B to A to C to A to B. Okay, so that is the, over here one oscillation is completed. Okay, so this is the time period of oscillation which is denoted by sign T of the oscillator. Okay, so starting from here, it goes to C, again come back to the original position A, then it goes to B, and then when again it comes back to A, that is one oscillation. So from that we calculate the time period of the oscillation. Okay, now next we go to what we called as frequency. So the definition of frequency is the number of oscillation completed by an oscillator in 1 second is called frequency of the oscillation. Okay, so I am giving this oscillatory motion. The pendulum or the oscillator keeps on moving, and how many oscillations are completed in 1 second? I am putting my stopwatch on. So in 1 second, how many oscillations it is completing? That is called frequency of the oscillation. Okay, so if we see in the diagram, the total motion B to A to C to A to B. So suppose I am starting from here, then B, A to C, then C to A, and A to B is one oscillation. Now what if, suppose I am starting from A to C, then back to A, C, and again A here. And suppose I am starting from C, then you tell me children how it will be. C to A to B, again back to A, and when it again goes to C, it is one oscillation. Okay, so like that, how many oscillations are happening in 1 second is called frequency of the oscillation. Now frequency, which is denoted by a symbol N, its formula is frequency is equal to 1 upon time period of oscillation, that is denoted by T. So 1 upon T. So frequency is the number of oscillation occurring in 1 second. Just now we have studied the unit of frequency is hertz. Very important, please note that. 1 hertz means there is one oscillation in 1 second. So in 1 second, when only one oscillation takes place, it is called as 1 hertz. And 100 hertz means 100 oscillations in 1 second. 10 hertz means 10 oscillations in 1 second. Okay, so time period is the same. The number of oscillations that are taking place in that particular second called or means that hertz. Okay, or that is how we calculate the frequency. Okay, I hope it is clear to everybody. Now, let's take a small experiment and see how the frequency or the pitch or the loudness of the sound is related. Now, we have taken a plastic ruler and I have already hold its one end on the table, as you can see in the picture. Now see here I have taken the picture or the scale in such a way that the larger portion of the scale or the ruler is off the table. Okay, now I am pressing the free end from here and releasing it. Then I will observe what will happen. Okay, you all know that the ruler will start going up and down. Okay, now you can see that press the ruler with your finger at such a point that it stops making any sound. Okay, so it will make that sound, not very louder, but it will make the sound. Then we will stop the sound with the help of the finger. Now second diagram, see, I have taken the ruler much inside. So almost half of the ruler is on the table and half is out of the table. Again I am going to give a jerk at this point. Again I will hear the vibrations or the sound that is occurring. Okay, then third case, what I will do is, as you can see here, more ruler I have taken inside. 3/4 part is on the table and only small, that is 1/4 part is out. Again I am going to give a jerk to this and again I am going to hear the sound. Okay, so what will happen is, in all the case sound will be there, but there will be difference in the sound. Okay, so somewhere the sound will be little louder, whereas somewhere the sound will be a little smaller. Okay, so we can see the difference between the first and the second and the third sound. Okay, and from that we can find the difference in the frequencies and the pitch of the sound. Okay, so what is that difference we will see later. Also take a note of what happens by further decreasing the length of the free part of the ruler little by little. Okay, so I will just keep on. Now here in this case it will be, sound will be more. Okay, then I am taking the ruler inside. At one point very little part is there, sound will be there, but I will not be able to hear that. Okay. Will a sound generated no matter how the ruler is kept on the table? No. The sound will not generated no matter how the ruler is kept on the table. Suppose entire ruler is on the table, of course the sound will not be generated. Is there any correlation between the length of the free part of the ruler and the sound generated? Yes, of course, there is a relation between them. Less length, few vibrations, low sound. More length, more vibrations, high sound. Okay, so when the distance was more vibration and high sound, as I told you, and as we keep on decreasing the distance, the length is less, vibrations are less, and sound is also less. If the ruler is plucked while it is held with 25 centimeter off the table, does it make any sound? That means the smallest distance. Yes, it will make a sound, but it will be very low. Okay, now let's take one more experiment. This is a pendulum. This is a metal bob that is attached to one end. Okay, and then I have measured the length of the thread in centimeters, and I have suspended the pendulum freely from a support. Now what I am going to do is I am going to swing the pendulum. Okay, so this is the way I am going to swing the pendulum, and with the help of stopwatch I am going to record how much time is required for 20 oscillation. Okay, so from here to here to here to here is one oscillation. Like that I am going to record 20 oscillations. Okay, and then what I am going to do is I am going to decrease the length of these pendulum every time and going to record the oscillations that are, or are going to require the time that is required for 20 oscillations. From this experiment, we will see that as we decrease the length of pendulum, the time taken to complete 20 oscillations will also decrease. Okay, so less length, less time it will take. So, the relation between the frequency and the length of the pendulum is, a pendulum with a longer string has lower frequency, meaning it swings back and forth less time. Okay, so with a long length or a long string, the oscillations will be fewer. Okay, so frequency is also less. Okay, and where the length is shorter, the oscillations will be more, or it will take more time, and the frequency will also be more. Okay, then what is meant by low frequency and high frequency? A low frequency sound has a low pitch, like the rumble of a big truck when a big truck is moving. That is a low frequency. On the other hand, a high frequency sound has a high pitch, like a whistle or a siren. See, when a whistle or siren rings, it really goes into our ears. Okay, so the frequency is very high. On the other hand, when the truck goes, sound is there, but it is not actually penetrating inside our ear. Okay, and in speech, women have higher fundamental frequencies than men. Okay, this is just for your information. Now keep the length of the pendulum fixed as 30, but varying the amplitude. Ensure the time required for 20 oscillation in increase. Now what I am doing is, the length is constant. See the diagram here. Everywhere the length is constant. What I am doing is, amplitude I am giving, or I am changing the amplitude. So it can be small, as you can see in the first diagram, or large as in the second diagram, or very large. Okay, so again I am finding the time period for 20 oscillations. Okay, so after this experiment, what I will see that the time period of oscillation T depends upon the length of the pendulum. Okay, longer the length or more the length, time required will be more. The time period of oscillation increases if the length of the pendulum is increased. This I already told you. More the length, the time required to complete 20 oscillations will be more. Okay, and the frequency remains the same even if the amplitude is decrease or increase. Okay, so frequency and amplitude doesn't make much difference. The frequency remains the same even if the amplitude is decrease or increase. Okay, so This all the things we have studied. Thank you very much.